Capacitors. Capacitors consist of two conductors that are not touching each other. It's a device that stores charge or electrical energy by separating the positive and the negative charges from one another. In class, we played around with some capacitors, this green thing over here, and we attached it to a hand Genicom. By spinning the Genicom, we were able to separate the charges and able to get one of the plates to become positively charged and the other plate to become negatively charged. And then we hooked it up to like a light bulb, and you could see it discharging the electrical energy through the light bulb and lighting it up. The work that was done in separating the charge ends up as electric potential energy stored within the capacitor. There are a variety of different types of capacitors. Capacitors are found in nearly all types of electronic circuits. Computer memories that are found in computers are very tiny capacitors that store them as binary codes of ones and zeros. Capacitors are also used in the photo flash units of a camera, where it can release large amounts of energy in a short period of time. They're also used in medical devices such as the heart defibrillator. In the upper part of your right screen, you can see that a computer keyboard utilizes a capacitor. When you press downwards, the capacitor spacing between the plates reduces, thus increasing the capacitance, which can be detected electronically. The simplest case of a capacitor which we will study is just simply a pair of conducting plates, having a cross-sectional area A and separated a distance d apart from one another. This is known as a parallel plate capacitor. In practice, these plates are just thin metallic foils separated a distance d apart from each other, and they can be kind of rolled up into a kind of like a paper sandwich to save space, and then inserted into a cylinder, such as these capacitors you can see shown in the picture here. Let's dive a little bit deeper and take a look at a PHET capacitor lab. As mentioned earlier, a parallel plate capacitor consists of two metal plates, one carrying a positive charge plus Q, and the other plate carrying exactly the same magnitude of charge, but it's negative, Q. One way to charge a capacitor is to connect it to a battery. So here is simply an uncharged capacitor, and there's no net charge on either one of these plates. So suddenly I'm going to connect the plate, the top plate to the positive terminal, the bottom plate to the negative terminal, and then going to set the voltage of this battery to positive 1.5 volts. And you'll notice that when I change that to positive 1.5 volts, let me do that once again, you should see that electrons are being pumped through the circuit, those arrows that you saw over here. This occurs because the positive terminal of this battery essentially pulls the electrons that were over here on this plate and pumps them through this battery over down to this lower plate, and this lower plate becomes negatively charged. And then this, consequently, will become equally positively charged, with the same magnitude of charge, except it's positive. Once the charging process is complete, then the voltage across the capacitors is the same as the voltage across the battery. Let me show you that by clicking over here with my voltmeter. Oops, right there. And I'm going to put this across the negative one and this on the positive, and you can see that's 1.5 volts, which is again the same as the battery voltage as well. Alright, at this point I want to develop the definition of capacitance. So what I'm going to do here is I'm going to pull out a meter for the amount of charge that is shown on the top plate, set at 0.13 times 10 to the power negative 12 coulombs. And I'm going to change the voltage here, and you're going to see that the plate charge is going to change. So as I lower the voltage, the plate charge lowers, and the voltage has gotten smaller. As I decrease the voltage more, I have less and less charge. As I eventually go down to, say, 0 volts, I'll have no plate charge on here. So there's some kind of relationship that exists between the charge on the plates and the voltage that is across the batteries. It appears that if I increase the voltage, I will increase the charge. As I keep on increasing the voltage, the charge gets larger and larger. So there seems to be some directly proportional relationship. But the best way to find out if that relationship does exist is really to plot a graph. So what I'd like to do right now is just very quickly plot a graph of the charge, the magnitude of the charge on the top plate versus the voltage that I'm establishing across the plates or across the battery. So using this animation, which you could do, go to the PhET website and click on the capacitor lab, you can collect your own set of data. So I'm just going to click along here, and you can see up at 0.46, and then I write down the charge, and I just keep changing this value, 0.71 volts, and then I write down the charge, and then again 0.883, and then I write down the charge. And I would like to produce a graph of charge versus voltage. Alright, so I collected some data from the animation, and I plotted charge on the y-axis and voltage on my x-axis. And my charge is measured in picocoulombs. By the way, this is the charge on each plate. And you can see that there's a nice direct relationship in here. Let me just make sure I set this so that the graph goes through the origin here. So I'm going to auto scale from 0 here. And you can see that that line pretty much goes right through the origin. And so there seems to be a directly proportional relationship between the charge Q and the voltage V. And so from this graph, we can then think about what capacitance is. You see, the higher the voltage we have, the higher the charge that we can distribute across each plate. The capacitance remains the same for the capacitor. The capacitance is really the slope of this graph. So the capacitance is really the proportionality constant of this graph. So you can see that slope right here, which is 0.08896 picocoulombs per volt. And so that slope, or that proportionality constant, represents the capacitance. And the units of coulombs per volt is known as a farad. So to rehash, going back to our notes, capacitance is equal to the ratio of the charge divided by the voltage. Now on the AP formula sheet, it's represented this way. Delta V, the voltage, is equal to the charge divided by the capacitance. So this C stands for the capacitance. The capacitance is measured in units of farads, and a farad is equivalent to 1 coulomb per volt. Typically, capacitors are measured in things called microfarads, which is equal to 1 times 10 to the power negative 6, or picofarads, which is 1 times 10 to the power negative 12 farads. And even maybe a nanofarad, which is 1 times 10 to the power negative 9 farads. So those are the typical units. You know, most capacitors are very small in capacitance. If you had like 1 farad of capacitance, that's a large amount of capacitance. Simply a pair of plates that would have, say, an area of like 1 meter squared that would be separated by maybe a millimeter apart, which that would have typically a capacitance of 10 to the power negative 8 farads. So that's like 10 nanofarads. So really, capacitance is not, you're not going to have like 2 farads of capacitance. That's unusual, I will say. So what is capacitance conceptually? Well, think of it like its ability to hold charge for a given voltage. If I were to have a different capacitor that had, say, a higher capacitance, the slope of this line would be steeper, so it could hold more charge for a given voltage. So for a given capacitor, the voltage and the charge are directly related to each other, but they do not change the capacitance of itself. Capacitance is only going to change if you change the geometry of the capacitor. So increasing the charge will increase the voltage, but it's not going to change this line. To change that line, that slope of that line, you really have to change the physical properties of the capacitor. So let's go back to our animation that we had earlier, the capacitor lab. So here it is again, and let's say we just disconnect the battery for now, and we probably don't need the voltmeter. But what I would like to do is now add in a meter called capacitance. You can see there's the capacitance of this capacitor. So what do you think would make this capacitance get smaller or bigger? Well, if we decrease the area of the capacitance, well, that doesn't really change it here because it's actually at the smallest value, but if I increase it, you can see that the capacitance gets bigger. Watch. As I decrease it, capacitance gets smaller. As I increase the area, I get more capacitance. If I were to change the separation between these capacitors, if I make them get closer, that increases the capacitance. But if I make the plates get further apart from each other, the capacitance decreases. So I kind of think of, let's say I connect this battery over here again. I kind of think of it like, like a parking lot. And that these electrons or protons, let's make this negative up here and put this electrons all up here now. And so when I increase the area of this, I'm basically increasing the size of my parking lot. So I can accommodate more charge or more electrons on that plate. If I were to decrease the distance between these two plates, that also increases the capacitance. You see, it's kind of like, well, the proximity of these electrons down from the protons here is quite close. So you don't have to work as hard when you move these electrons back and forth from one plate to another plate. So if the plates are pretty close to each other, then the capacitance is easier to achieve. So you have a higher capacitance in a case where the distance is smaller. So essentially you can park more electrons more easily if you have these plates closer together to each other. So the formula for determining the capacitance of a capacitor or parallel plate situation depends on the area. We saw that the capacitance was directly proportional to the area because as you made the area bigger, you got a larger capacitance. And we saw that it was inversely proportional to the distance between them. So as you made the distance get smaller, the capacitance increase. So hence, we get this formula C equals epsilon naught, which is a constant of proportionality, known as the electrical permittivity, or the free space permittivity, times the cross-sectional area divided by the distance. Now this equation right here that I've just written is the equation for a vacuum or air filled between the two plates. So if you just simply have air or a vacuum between the two plates, then you can use this formula. You notice over here this more general formula has this variable K. Actually, technically, it's a kappa. And that kappa is the dielectric. It's due to the substance that you could put in between the plates. You see, one of the problems that we have when we just simply use two plates with, say, dry air between them, the electric field that is established between the two plates. I guess we should show that. Let me just take a quick look at the animation again. Here we go, back to that animation, but in this case I'm now going to show the electric field lines between the two plates. And so this electric field between the two plates breaks down at about, say, 3,000 volts per meter. And it's even less than like humid air. So the breakdown allows, like, say, sparks to jump from one plate to the other plate, and so then you lose charge that's stored on the plates. So one way of overcoming this problem is to use a better insulator than air between the two plates. And that insulating material is known as a dielectric. So let me should click on this tab, the dielectric. And so here's a substance I can put in here, and that is going to increase the capacitance. You can see now if I put the capacitance on here and I insert it, the capacitance increases for the capacitor. And so by inserting that dielectric within the plates, it's basically an insulating material. It could be rubber, glass, or wax paper. And that basically increases the capacitance. Watch as I charge up this capacitor, and then I'm going to show you the electric field lines, and then as I insert the dielectric within it, it changes the ability to store charge on each of the plates. It also affects the electric field between the two plates as well. This dielectric constant, back in our notes here, is represented with a capital K. Well, it's technically the Greek letter kappa. And so kappa is known as the dielectric constant. Now, for a vacuum, kappa is exactly equal to 1. If you're looking at air, it's a little bit bigger than 1. It's like approximately 1. So that's why if you're dealing with a capacitor that is either a vacuum or air filled, you simply do this because kappa is 1. So it just reduces to this equation over here. But when you take other substances that are like paraffin paper or rubber between the plates, you increase the value of kappa, and so kappa has a value that is greater than 1 for these different dielectrics. So to summarize, the dielectrics basically increase the capacitance of the capacitor. They allow it to operate at a higher operating voltage, and they also kind of support between the two materials so that these two metal plates won't touch each other. So they kind of provide a mechanical support so that there's not going to be sparks jumping from one plate to the other plate by accidentally touching each other, for example. And this epsilon naught is just another number that called the electrical permittivity, or sometimes called the vacuum permittivity, or the permittivity of free space. Its value is 8.85 times 10 to the power negative 12 farads per meter. It turns out that, remember Coulomb's law, that K that we were using, and KQ1, Q2 over R squared, say in electrostatic force, that's equivalent to 1 over 4 pi epsilon naught. So you can see the relationship with Coulomb's law, for example. So you've seen the formula relating the capacitance to the charge and voltage. You've seen how capacitance is related to the geometry of a parallel plate capacitor, comparing to the area and the distance, and the dielectric constant. And now let's talk about how the electric field is affected within the capacitor, and also the stored energy. Let's go back to our animation with the capacitor lab. See, the electric field of a parallel plate capacitor, let's click on the electric field lines, nothing right now. Well, I've got to establish a voltage. The electric field that is established changes, you see, in here. Well, I guess I better come up with some kind of electric field detector. Let's put that right over here. And so this is showing you the direction and the magnitude of it. As I change the voltage, it seems to have an effect on the electric field. So voltage affects it. And we can also see how the plate charge changes it. So the plate charge is also changing with the electric field. So we need to define what the electric field, how does that vary? Well, it turns out that the electric field, E in here, is equal to something called sigma divided by epsilon naught. Epsilon naught I introduced earlier. So sigma is known as the surface charge density. It's basically the amount of charge that is on either one of the plates divided by the cross-sectional area. So it's the charge per unit area of the plates. Substituting this equation into here, we get E is equivalent to Q divided by epsilon naught times the cross-sectional area on the bottom. Take a look at this. Now if I were to increase the area of this, you can see that the electric field is not changing. I wonder why. Let's say I disconnect the battery and try that. If I now change it, oh, it does. Because before, when I connected the battery and I changed the area, charge were moving back and forth through the battery. But if I disconnect the battery and there's no route for the charge to go around from one plate to another plate, and I were to change that area of the plates, it seems to affect it. So if I make the area bigger, the field gets weaker. If I make the area smaller, the field gets stronger. Let's connect the battery again, and let's see how the electric field varies with voltage. Looks like as you decrease the voltage, you decrease the electric field, and as you increase the voltage, you increase the electric field. Earlier in the notes, we had derived the formula E is equal to the change in voltage divided by the change in R, or X. And technically we were using the absolute value of that because there was a negative in here. So it's really the absolute value. This was known as the potential gradient. We called the electric field the potential gradient, the slope of a potential versus distance graph. So you can see that the electric field is directly proportional to the voltage. So if I decrease the voltage, then the electric field decreases. So earlier I showed you these two graphs, or two equations, where you have E, the electric field depends on the charge divided by the area times the permittivity of free space, and the electric field depended on the voltage divided by the distance between the two plates. And I'm using a D here now because that's what's shown in the picture here when we talk about separation between the two plates. So if I equate these two equations, we get this, and then if we rearrange, we get this, where the charge is directly proportional to the voltage. Which brings me back to my original graph that I showed you earlier. And we saw that there was a direct relationship between the charge, Q, and the voltage, delta V. And so this, right here, represents the slope of the graph. And this is known as the capacitance. This formula of the electric field being directly proportional to the charge and inversely proportional to the area is mentioned right over here at the very end of my notes. And this brings me to my last piece of this video, and a rather long video, the energy stored in the capacitor. I talked about that earlier, that a capacitor not only stores charge, but it also stores electrical energy. Well, the energy stored in the capacitor can be found by finding the work done by the battery and separating the charge. Let's revisit our graph. Going back to our charge versus voltage graph, we can find the work done in separating that charge by taking the area under the curve. That's this integral button right here. So if we were to extend that area all the way to the very beginning, which I can't seem to do, you would get this nice big triangle. So that shaded area represents the energy that's stored in the capacitor. That area is equal to the stored energy, which we represented with a U, with a little subscript C for capacitance, or capacitor, which is equal to 1/2, because it's a triangle, times the base times the height. The height is the charge, Q, and the base would be the voltage, delta V. So hence this is the equation for the energy stored in a capacitor. Now don't confuse this with the other formula that you learned in the formula sheet. Delta U equals Q times delta V, and that's the amount of electrical potential energy that's lost when a charge, say, moves through a potential difference of delta V. You'll notice that this one has a factor of 1/2. That's because it's a triangle in here. So if this helps you, you could kind of think of this as like the average voltage is going to be half of the total voltage. Back to our capacitor lab, we can see if we bring up the stored energy, that's going to change if you change the separation or change the plate area, because you're really changing the capacitance. And if you change the capacitance, you're going to change the slope of that line, which means you're going to change the area under that curve. You also change the stored energy if you change the voltage. So a higher voltage will store more energy. So back to the notes. I've written the formula that is shown in the AP formula sheet. The stored energy in a capacitor is 1/2 times the charge in one of the plates multiplied by the voltage across the plates. You can get this formula by replacing things in. Like, let's say you know that the capacitance is equal to Q over V. So therefore you could, if you like, say I would like to get rid of Q. So if you rewrite Q, it will be C times delta V. And then if you replace that into this equation, replace that with C times delta V, you will get 1/2 C times the change in potential difference squared. So there is another formula you could write as well. It's, I believe, Q squared divided by 2 times the capacitance. And that would be achieved if you replace instead the voltage with charge divided by capacitance. If you replace the voltage with Q over C, you're going to get a Q squared, and then you'll get the capacitance on the bottom. So there are a variety of forms that you could write the capacitance formula in. These are the two the way it's shown on the AP formula sheet. And I think this is already a rather long video. Let's get some